Everybody, can you see my screen?
Yes, doctor.
The title is Active Power Control.
Yes.
Okay. So, the main thing of the transient stability control is the active and reactive power control. And of course, between these two active and reactive power controls, active power is important, especially if the power network has synchronous generators. So you see, that's why I have written that during any major disturbances in a power network consisting of mainly synchronous generators, it is essential to control the active power as it goes low. So you remember that before we talked, when there is any fault in the power network, so active power goes low. And if the system has mainly the synchronous generator, so active power control is very important. And before we talked, if there is induction machine, then reactive power control is dominating. That is important. And if there is mixture of synchronous machine and induction machine, then both control are important, both active and reactive control. So today we will be looking the active power control, assuming that the power network has mainly the synchronous generator. So at this point, we are assuming that there is no induction machine. So the thing is that before we discuss this equation once, it is called swing equation, phi A equal to Pm minus P. So ideally during steady state condition, the difference should be zero. So meaning that Pm is the mechanical input power that is coming from the prime mover, from the turbine system. And P is the electrical active output power. So this is the power that is being consumed by the customer. So we are assuming that there is no loss in the system ideal, then Pm should be equal to P. Now, as we are discussing the active power control during any major disturbance means that three-phase short circuit or just three-phase short or three-phase to ground fault, double line to ground fault. Any of those faults are treated as major disturbances. So that time what happens? P goes low. So, but we are assuming that P is constant because that is coming from the prime mover. Of course, there can be any issue in the prime mover side, but typically input remains constant. Consequently, rotor starts moving at constant speed. Consequently, it provides the constant power. In majority cases, problem is in the network side, electrical side. So therefore, whatever the type of the disturbance is, P goes low. Now, active power control means we have to return back P value to the original position or close to the original value. So for example, a system, a network was drawing 100 megawatt. Customers are consuming 100 megawatt. And during fault, that P goes low. Goes low means maybe you can assume even zero. Now, because it was providing 100 megawatt power, so you have to, active power control means you have to do something, you have to provide some means, some methods in the network side that can provide that close to 100 megawatt or if possible 100 megawatt. That is the meaning of active power control. So the thing is that because P is going low, so you boost up. Or it might happen, for example, not short circuit, not double lines ground fault, 3LZ ground fault, but you injected some load. For example, there was 100 megawatt in the system and system was balanced, but you put another 10 megawatt. You created additional load. You put additional load. So then it is going over. In that case, what will happen? Because the result will be negative, so system will decelerate. So in that case, your goal will be to reduce the active power. Again, that is the active power control. So therefore, in either way, when the P goes low because of any fault or some customers injected some load and then P is going high. So in that case, you have to reduce P. On the other case, during fault, you have to increase the P. That is the meaning of active power control. Now, the thing is that how to do that? What you will do? Because as I said that consumers are consuming power, and then because of the fault, at the fault point, voltage goes very low, and then whatever the current increase, the fault current, the multiplication goes very low. But then I am saying you have to increase the power. So how to do that? So that's why there are several methods. I mean, in this class, we will be covering couple of methods. So as I have written, one of the important methods, a very popular method, and very simple and pretty interesting method to control the active power is called dynamic braking resistor. So this dynamic braking resistor will provide active power. It will boost up, it will increase the P during fault situation so that system balance come back, system stability come back. Therefore, now that's the question that we'll be looking today. What is that dynamic braking resistor and how it works in the system? So here you see, for you I have written, what is braking resistor? The braking resistor is a large load usually placed at the terminal bus of a synchronous generator. So for example, everybody say this network, just I have shown one synchronous generator and there is a transformer connected and this represents double circuit transmission line. Just keep in mind, although I am just showing only one line, like it's a single line, but in fact there are three phases. So this is called single line diagram. And ultimately, the generator is feeding to the infinite bus. Infinite bus means the bus where the voltage and frequency remains constant within a certain limit. So, and then you see the application of the braking resistor. Can you see that there is a switch, and with the switch that braking resistor is connected. So this is the thing. Therefore, once again, I have written down the swing equation for you. As I said, during fault, P will go low. Now this braking resistor, I mean shown in this figure, and it is connected right after the terminal of the transformer. If you don't connect any transformer, then even you might connect the resistor here right at the generator terminal. But in most cases, after the transformer, I mean at the grid point, it is connected. Now, what it will do, you see there is a switch and you can guess, easily you can guess, this is an automated switch that this will be connected during fault. So what it will do, if you connect a resistor, then what the resistor will do, it will consume power. So therefore, for example, there is no braking resistor and there has been any fault along this line or this line, and then P will go low. And then the high current is flowing in the network. So at that time, if you connect, if you switch in this braking resistor with the help of automated control, then what will happen? Current will come this way. And then, this is simply a linear resistor. It is nothing but a R. So what will happen once current will flow? I square R. Now, if you see, you remember, as I said few minutes back, that for example, initially that P value was 100 megawatt and that became close to zero. Now, you have to design the braking resistor R value such a way so that I square R during fault condition, when current is flowing through it, I square R value becomes 100 megawatt. So you see, because this resistor, simply a resistor, is a very good load. So I square R, or even if you know the voltage where V square over R, the same thing, that will boost up the P value. Now the thing is that after automated switching this on, once the system stability will come back, I mean initially system will be accelerated, speed will go high, frequency will go high, voltage will go down, and of course power will go down. When every parameters will come back to an acceptable equilibrium position, then again you disconnect it. Again you disconnect it. So therefore, function of the braking resistor is only work during the fault moment to boost up the PA value. That's why you see the braking resistor is a large load, usually placed at the terminal bus of a synchronous generator. And what it does, during large disturbances, the braking resistor can control the accelerating power in generator and thus improves the transient stability. Accelerating power means when the P goes low, we are assuming Pm is constant, so Pa has positive value. The Pa is the accelerating power. Acceleration means that generator speed goes very high. That get accelerated. So therefore now we have to brake. That's why it is called the braking resistor, because it is braking. It is coming down the speed and hence the frequency and ultimately the transient stability. So you see, very simple method. So now, so everybody so far, so are you fine? Could you follow me?
Sir, I have a doubt.
Sorry?
I have a
Hello?
doubt.
So what you said, Venkat?
I have a doubt, sir.
So I could not, I could not clearly hear you.
Yeah, I have a doubt, sir.
What is that?
So, like, using this control method, we are just going to like balance the grid, or also we can compensate some power.
So
Is there any compensation like?
this compensate the fee, ultimately the transient stability maintained. And then transient stability maintenance means the, of course, the speed, speed will be accelerated, that will come back. And if speed comes back, then frequency will come back. And at last, the voltage will also come back. So therefore, with regard to your question, first it will compensate the speed and then frequency. And of course, because it is consuming power, at the beginning it is controlling the fee, finally it will control the voltage. Now, so do you understand? Yeah.
Yes, sir. So ultimately, the goal is to balance the grid, right?
Yeah, yes. Ultimately, goal is to balance the grid. So therefore, you see, as I told you, whatever the location of the fault is, impact goes to the generator.
Yeah, yes.
Yes. So therefore, you see, because this is a rotating machine, a rotor is rotating, and the for the whole network, the frequency 60 hertz, that is actually determined by the generator. So
Yeah.
because if the shaft goes accelerated or shaft goes decelerated in case of the negative value, then your frequency will change. So ultimately,
Yeah.
throughout the network, even customer side, frequency will be changed. Therefore, first you have to control the machine. You have to return it back. For example, it was rotating 3000 RPM. You have to return it back. Only then it can provide the required frequency. So therefore, ultimate goal of this resistance, that's why there is a switch. So okay, can you guess why there is a switch? So
So
therefore,
remove the excess amount of the current in the network.
yeah. So therefore, I mean, you may argue that no, okay, I will be always connecting it because anytime in the system there might be fault. But will it be wise? Wise? It will be wise
No,
decision? No. Why? Why?
because losses may increase.
Because it will consume all. It will always consume the power, right? Yeah.
Yeah, yeah.
Exactly. Everybody, could you understand?
So most of the power will be going to the ground.
Exactly.
That is a
Always.
consequence.
And as I said you that it is designed according to the P value. For example, if the consumers consume 100 megawatt, 200 megawatt, it depends on the network where it is connected. Accordingly, its resistance value is designed. So that I square or V square over R makes up that amount. So it's a huge resistance. So therefore, if you always connect it, then it will always consume power. And then braking resistor cannot do anything. It cannot, generate any power. It cannot provide any power. Only it can consume power. So therefore, everything will go in loss. So even you cannot always connect it. So that's why I say it is automated switch. Once there is any fault, the signal will come. Okay, get it connected. And again, it will understand the status of the system. When the system stability is maintained, then again it will be disconnected. So therefore, now then easily you can guess that are there any other drawbacks? Okay, I understand that there is an automated switch. It is opening and closing, but could you guess what could be the other problems? As I said that it will handle this amount of power. So with regard to that, what could be the other problem, other possibility? So everybody, do you understand my question?
So what was the question, Dr. Ali? Can you repeat it again?
The question is, I think you understand the operation of the braking resistor, right?
Yes.
So then I said that it is designed, it's a fixed value, it's a fixed resistance. Just an example, for example, it has 10 ohm, just an example. So therefore, when automated switch is getting closed, this means that 10 ohm is working, right? Yeah. Then when disconnecting, then that is disconnected. Now, my question is that, do you think that that fixed value will work always? Because I said that this will compensate this peak. And I said, okay, if it is 100 megawatt or 200 megawatt, it is designed such a way so that it can compensate that amount. It can provide that amount during fault. So now the question is, the 200 megawatt, 300 megawatt, considering the viewpoint of the maximum power flow capability. This means that is the maximum value. Now, for example, fault may not be always three-phase to ground fault. Fault could be simply single line to ground fault or line to line fault. There is severity or there is ranking of fault. So when it is single line to ground fault, two phases are fine and only one phase is unhealthy, then do you think that the same amount of power is needed to provide?
No.
No, definitely no. But then this is the fixed, you see. Even I did not give any variable sign. That is the thing. So this
So there will be a possibility for damage of the braking resistor if it is fixed value.
Exactly. If it is fixed thing, and I said it is automatically closed and then automated, so that is fine. It is automated. That is fine. Everybody want automation, but then this value is fixed. So what will happen? First of all, always the fault is not the same. Not always like severe situation. Only one LG fault. So in that case, too much high power injection is not needed. That is one thing. The second thing is, sorry, yes, Manoj?
Can't we make it like adaptive kind of resistor or kind of varistor so that it will, give fixed power according to the, fault or something?
Exactly. So therefore, that is, I'm coming in the next slide here. So I'm answering to your question, and I will fully follow you. What you said, that is correct. So this means that this control thing should be some adaptive, and there should be some good mechanism. It is not just like, okay, it will collect signal, there is fault, it is closed and open. There should be something in the switching. So you can keep it fixed, for example, on ohm or 10 ohm, but then there should be some mechanism here, power electronics based control, that can control the power consumption. Resistance value can be fixed, but you have to control the flow of current. For example, during 3LG fault, if 100 ampere flows, then during 1LG fault, let flow only 5 ampere. So this means there should be some controller here, sophisticated control mechanism, of course automated, plus some power electronics based control that will control the flow amount of power. So that like I square R, because I am keeping R fixed, so then I value change, then this consumption will change. So therefore it depends on the type of the fault. Accordingly, it will work well. So therefore, like everybody see the next slide. Can you see? I am showing just one example. Now see this resistance. And what I have connected here? Thyristor circuit. Thyristor circuit. And I am putting a control mains. So not just only the power electronics. What I am doing? This is the generator. As we discussed that during fault, generator speed will change, right? So therefore, I am assuming I have a control. It could be simple proportional integral controller or fuzzy logic based controller. I have a controller. And because I am, everybody look, because I am using thyristor circuit, so you know that thyristor has the triggering angle or the firing angle. So you have to control that triggering angle, firing angle. Only then you can control the flow of the current. When it is severe fault, uh, maintain the high value of current. And when it is less severe, 1 LG fault, maintain very low value because this is fixed. So this means that we have to control their gate. So this means this is the triggering signal. So therefore, whatever the control structure is, you need not to be worried what is the control structure. Just assume that it's a controller. Even may not necessarily only fuzzy or PI. It could be other sophisticated controller. There are lots of controller. So you assume that there is a controller, I need on input and I need the output, but I will send that alpha to that to trigger those thyristor circuit so that it can control. This means definitely that for alpha has a range, like typically alpha is 0 to 180 degree. So everybody, do you understand that firing angle or triggering angle that is needed by the thyristor?
Yes, certainly.
Yes,
Yeah.
sir.
So for example, you have a waveform sinusoidal, but it may not work from the zero. Always there is some sort of delay. So that is called the firing angle or triggering angle. And then the maximum value is 180 degree. 180 degree means almost this is off. No current will flow. And alpha 0 degree means the full conduction, 100% conduction. So, and then as you can see, what I am taking control input del omega. What is del omega? That is speed deviation. What was my reference speed of the shaft system and what is my speed during transient condition, during fault condition. So let's progress, let's give that difference as an input to the controller. And then input will progress, there are lots of parameters to be tuned and it will produce the alpha. So therefore you see, everybody see, because the del omega is dependent on the type of the fault. If it is 3LG fault, then definitely del omega value is highest. When it is all LG, it is small. Accordingly, it will produce the control output. So meaning that during 3LG fault, it is the expectation that there is full conduction, so that alpha value goes 0 or close to 0. Whereas when it is single line to ground fault, it is the expectation that alpha value will be maybe 80 degree, maybe 50 degree, or maybe 100 degree, or maybe more. Or even it might be close to 180 degree. So that very little current goes. Because at that time, a small consumption is needed. Therefore, you know, whatever current goes, I square R, it will work in that fashion because this is fixed. So therefore, main goal of this arrangement to control the flow of current. And that's why you need a controller. Now, now we will be looking this thing that how it controls and what will be the governing equation. Then you will get fun and we can solve some numerical problem. So go to the next, just everybody keep in mind. As you can see, there are two thyristors back-to-back connected. You see, during positive half cycle, this thyristor will arc. During negative half cycle, this thyristor arc. In that fashion, it arc, you know, for a waveform, because really there is waveform here, sinusoidal waveform, positive and negative peak. So during positive peak, this will arc. During negative peak, this will arc. In that way, there will be continuous operation. And this is, keep in mind, this is only for phase A. So this means you need another 2 for B phase, another 2 more for C phase. So therefore, everybody see this arrangement I have written. This is for phase A, those two thyristor on breaking resistor, and then it is grounded. So this arrangement for phase B, this arrangement for phase C. So therefore, you see total there are 6 thyristor, 1, 2, 3, 4, 5, 6, and 3 breaking resistor for 3 phase. So now what happens? This is the governing equation. How much power is consumed by each of the breaking resistor? This is the amount. P breaking resistor, Vg square over pi RBR. RBR is the resistance value. As I said, for example, 1 ohm, 2 ohm, whatever it is. What is the Vg? Vg is the voltage here, RMS voltage here, Vg. And then pi minus alpha. Alpha is the firing angle of the thyristor. Then 0.5 sine twice alpha. So, next slide, I will show you how I get that on. I will show you the derivation, then immediately you can understand. And what is the constraint for the firing angle? Firing angle 180 degree means no conduction. 0 degree means full conduction. So therefore, easily you can guess when it is 180 degree, 180 degree means that is the pi. So therefore, put pi here. So pi minus pi is 0. And then there is sine twice alpha. If you put alpha 180 degree here, 360 degree, sine 360 degree is 0. So therefore, ultimately the PVR will be 0. But on the other hand, look the 0 degree. So therefore, sine this will be 0, this portion, but alpha is 0. So you are getting pi. You see, pi cancel. Your PVR value is Vg square over RVR. Which you know, like ideally V square over R. So that is the maximum consumption. And then depending on the alpha, because these factors are multiplied with this, this portion will play the role during 1 LG fault, 2 LG fault. Accordingly, by using this equation, with the help of control of alpha, you can control the power consumption value. And then that will maintain your stability. So now, like how I got this equation, I have made a derivation for you. You see, everybody see, for example, the point where the breaking resistor is connected, I am looking the voltage and current profile. So everybody see, I have assumed, okay, V equal to Vm sine of omega t. And what will be the I value? I is Vm over R, right? So because there is resistance, Vm over R, then sine omega t. And then I am just showing the plotting. This is omega t axis and this is voltage or current. For both this axis. So if this is voltage curve, then definitely current will be smaller because it is Vm over R. That's why I have shown like dot dot dot. The dotted on is the current. And you see, I have shown the alpha. This alpha means at the very beginning it is not working. It takes some time. That alpha is the firing angle of those thyristor. So now based on that, I know voltage and current. So I can calculate what is the average power. So that's why what is the average power? So that's the basic definition from circuit standpoint. 1 over t total time period of this one and 0 to t and then Vi d omega t. Instantaneous voltage multiplied by instantaneous current, these values. Now, so you all know that you cannot make average or you cannot integrate over a full cycle because here it is positive, it is negative. So your average will be 0. That's why for sinusoidal, always you have to make average over the half period. This means from 0 to pi, 0 to 180 degree. That's why you see in the next line I have changed t means 1 over pi. And it will not work from the 0, although I wrote here 0 to t, but I changed alpha to pi. From here to this point. And then now I substituted V and I values originally I defined here. And everybody see what is happening? Just look the calculation 1 over pi, this Vm multiplied by Vm squared, R is going in the denominator, this pi is this pi, and then what you will be getting? You will be getting sine square omega t, right? But then you cannot integrate the sine square omega t. So what I did, I multiplied by 2 and that's why I divided by 2. So 2 cancel, it is the same. What is the goal? Because 2 sine square omega t is 1 minus cosine 2 omega t, trigonometric identity. And then I am just integrating. So because it was 1, so after integration, I got omega t, and I put those definite integral limit alpha to pi, then minus cosine 2 omega t means sine 2 omega t, and then 2 is coming here. Again, I am putting the limit there. So ultimately, I got this one, Vm square over 2 pi r, pi minus alpha plus half sine 2 alpha. But then in the next line, so everybody says this Vm was actually this Vm here, the peak, but I want to express in terms of the RMS quantity. So I wrote V RMS square. This is my equation. Vm, this Vm is root 2 RMS. So what I am getting, there will be 2 here, 2 cancelled, and V RMS square over pi r, and then this. So this is the equation that actually I wrote down here. This is that equation. So therefore here I have used the symbol Vj, but you just remember this Vj is the RMS value, yeah. And RBR is the resistance, and alpha is the firing angle. So therefore by using this equation, you can calculate what is the power consumption, how much power is needed to be consumed by the resistor to maintain the stability of the system. So everybody, could you follow me so far?
Yes, sir.
Yes.
Yes, certainly. Yeah.
So therefore, what I would recommend you, everybody, please write down this equation upfront. Soon, in a couple of minutes, we will be solving some problem. So everybody, at this moment, you write down this equation in your note. And again, you need to be ready with calculator. You will be solving some problem. You see, this is Vg square over phi RBR. And keep in mind, this is the RMS voltage. This is the RMS voltage. And then in parenthesis, pi minus alpha plus 0.5, or you may write half sine 2 alpha. And then unit is in watt. Yes. So everybody, have you written?
Yes, certainly.
Okay. Okay, later again I can come back. Okay. So now the thing is that, and now concentrate the construction. Now you see, for 3-phase, I have, total 6 thyristors. That is fine. That is needed. But I have 3 braking resistors. Therefore, there is other approach that, okay, I might need 6 thyristors, but can I use only a single resistor? But then definitely, because it is designed by the phase, so you cannot use on resistor. Definitely for 3-phase you need 3. But then research went on, and then we looked what I can do. So how we can use only one resistor? What can be the topology? While there will be 6 devices, power electronic devices. Therefore, see that I have one arrangement here. Everybody see? A rectifier control braking resistor. Rectifier control braking resistor. This means, everybody see, because I have A phase, B phase, C phase. So why not using a rectifier? So, and then control rectifier, of course. So you all know in the rectifier you need the 6 thyristor. And then because rectifier is making DC, and then you can put only on resistor. So do you understand? So the previous approach was, it was the AC. both this side and this side, both side as the AC. That's why for three-phase you need a three braking resistor. But then in this approach, because you are converting AC into DC, and DC has only like two terminal, positive and negative, so you can connect only on braking resistor. So therefore, what is the advantage of this system? You are able to use only one braking resistor. Now, of course, you have to design it properly so that it works for all types of the faults or all types of disturbances. But what is the benefit of this approach? That definitely you are saving the cost. Now you may argue that, okay, I have three different phases. Probably the size of this one much smaller than having a simple one. That is true. That may be true. Or that may be right. That you may need a huge size of resistor, but still it is cost effective and it requires less maintenance, because in real practice, this has like huge size, like 1000 megawatt. In Oregon state, it is called the BPA, Bonneville Power Administration. I'm not sure you know or not. You can Google BPA, Bonneville Power Administration. They have this system, and they use 1400 megawatt braking resistor. Can you imagine 1400 megawatt braking resistor? So this means 1400 multiplied by 10 to the power 6. So it's a huge. Therefore, time to time, you need some maintenance of this braking resistor. So when it is 3 in number, then definitely it requires, that long maintenance. So therefore, compared to that, when you have only one, size can be somewhat bulky as compared to each of them, but still it requires less maintenance. And overall, it is like kind of cost-effective approach. So therefore, you all know that how it works, because this is rectifier. It follows this equation: VDC 3 Vm by pi cosine of alpha. So this means this side is AC and Vm is the peak to peak line voltage of the input side of the AC side. And then in this side, you will be getting this amount of DC. And once you get the DC, then what is the principle? Just, P equal to V square over R, basic equation. So this means that here the main thing, controlling the alpha. So by controlling the alpha, you have to control the VDC value. And then accordingly, you can control the power consumption by the resistor. Now, there is other approach, with the help of chopper rectifier control braking resistor. So what is the approach? At first, and then in this case, rectifier is not controlled, but chopper circuit is controlled. That's why rectifier is diode based. It is not there, not thyristor. So what is happening? First, you are converting AC into DC, and you need to get a smooth DC. That's why you are putting a capacitor. And after that, this CS means that is the chopper circuit. You just need to on and off control, duty cycle control of the chopper circuit. Meaning that this is the DC to DC control, because already this portion is DC, so you are controlling a DJ at DC. So DC to DC control, which is called chopper based control. And then once you get the DC voltage, then the same principle, P equal to V square over R. Now, at the beginning, you see I have defined VDC prime, this voltage, which is the first DC voltage that appears across C. And then the voltage, the actual voltage across the braking resistor, which I have defined VDC. So therefore, see the first one, V prime DC, 3 Vm by pi cosine of alpha, but I have put it uncontrolled. Uncontrolled means they have the full conduction. Of course, diode has also the firing angle, but I am assuming full conduction. Alpha is 0 degree. That's why cosine 0 I did not put, because that is 1. So once I got 3 Vm, then you see, this is the duty cycle of this chopper device. So duty cycle is output voltage divided by input voltage. So your V prime DC is the input, and VDC, the voltage that appears across the braking resistor. So finally, with the help of duty cycle, you will be getting VDC. Then once you get the VDC, then you are fine. This means here the main control will be duty cycle. This means you need a controller, I mean similar to that one, that I was saying. You need a controller in each case. You have to, your input will be del omega, and you have to produce either alpha or the duty cycle. Then that will be controlled. So therefore, according to this approach, you have to control the duty cycle from that controller. And then what is the benefit? The benefit is that instead of 3 braking register, you are able to use only 1 braking register. So therefore, these 3, devices are popular. This thyristor control braking register, and then this one called the rectifier control braking register, and this topology is like chopper controlled braking register, chopper rectifier control, because there is both rectifier and then chopper circuit.
So Dr. Ali, I'm sorry.
Yes, please go ahead.
So which one is the mostly used in the university? I mean, in the industry, sorry.
In the industry, you see, this is very old concept. 1949, you know.
Pretty old.
Yeah. So the first application one is Russia and Japan around 1949, and then later in the United States, Australia, and somewhat in India, so far. So this is very popular, very old technology. So this is the widely used on this one, the thyristor based. But later in some small scale application, this has been used. This one, the rectifier controller. Yes. So therefore, for small scale application, this one is used. But mostly, as I mentioned, those countries, and as I said, that Bonneville BPA. I mean, in just a moment. Hold on. Right now, you can Google this one, BPA. Everybody, you can Google BPA. It is called the like Bonneville Power Administration. It is in Oregon State, in United States. They have that braking register. Also, you can Google this one. This river transmission system located in British Columbia, Canada, Vancouver. So they have, I mean, in North America, these are the 2 places that use the braking register. And as I said, that BPA, Oregon State, they use 1400 megawatt braking register. It's huge. So this is widely used, but they use that thyristor based system. Did you get it by Googling?
Yes.
Yeah. So yeah. So it has real application. Sometimes in case of wind generator system also there is some application, but the size of the resistor is small. It is not that big. Okay, so now, so everybody please write down this equation also. Everybody write down this equation. So this means that you will be using this equation when you have rectifier control braking register. So it depends on the problem. By reading the problem, you can understand which equation to choose. So you remember in this case, first you will be converting into DC voltage by using this equation, and then you apply the power equation. This is, I mean, common equation, you all know. So in my, PhD study, when I was a student like you, that in 2000, 2001, about 20 years ago, I studied this system well. So even in my simulation, I used a lot this braking register. And if you go just Google my name, or if you just Google braking register, then definitely you will get my name in several publications. Have you all written down this one?
Yes, Dr. Ali.
Okay, very good. Then now write down this one. Now write down, I mean, in case of chopper rectifier control braking register, give the title this one, and then of course, you know that these slides will be available in the class lecture as a PowerPoint file and definitely as a video. But now you write down these equation to solve the problem. So therefore here, this is V prime DC, 3 Vm by pi. This means this one is the first DC voltage that appears across the capacitor, and then finally at the terminal of the braking resistor, which is the VDC. So that is D multiplied by V prime DC. And then again, the power equation is the same. This is, you know, that very popular and widely accepted methods and the simple method, you know, because you see it's a simple resistance. The only that you have to design this portion, power electronic portion, then you are fine. So is everybody done?
Yes, Dr. Ali.
Okay. Okay, now you need the calculator. Everybody read. There are 3 problems that you solve the problems based on the knowledge that you learned using those equations. So for example, everybody see the first problem. A 10 MVA 5000 ampere single phase synchronous generator. I'm just showing the single phase generator for the first problem. Employs a thyristor based braking resistor connected in parallel at the terminal of the generator in order to improve the transient stability of the system. What would be the value of the braking resistor if the thyristor has full conduction and 10 megawatt power is dissipated through the resistor? That is the question. So therefore you all solve and let me know the what answer, what resistance value are you getting? So therefore, everybody, can you guess which equation to use?
The last one with the, because that has the full conduction.
I think thyristor controller, page number 4.
But what else? Can you see what it says? It says thyroid. Oh, can you? Okay, everybody, can you?
The first one.
Can you please read number 2 or just read number 2? No, Manoj, please read number 2 as well.
Oh, okay, 6 poles. That means we have to use the rectifier best.
Yes.
Yeah.
6 thyroid rectifier, but in the first problem that does not say that.
So we can use the last one or the first one? I don't know.
No, the read the last problem, number 3.
Okay. 3-phase synchronous into 6 poles on control. On control means we have to use the last one. Not this one. Pretty much sure.
Therefore, the first one does not say that it is rectifier. It does not say it is uncontrolled. So, and it just says, you see, the second line, thyristor based braking resistor. This means just traditional thyristor based. So you have to use the first equation.
Mhm.
That's why I have, you see, the problem statement is the same, but 3 differs in terms of the technology. That is the key point. Everybody, could you follow me?
Yes, sir.
Yeah. So like what Manoj was telling and I was explaining in response to his comments or question. So therefore, for first problem, you have to use the first equation. This means, everybody see, this will be your equation for that one, for the first problem. So, and then you already have written down that equation. Now you solve it. And you let me know that what resistance value are you getting.
Dr. Ali, is it 0.4?
Sorry, how much you said?
0.4?
It looks like the wrong.
Okay.
Can you please try?
Let me.
Yeah.
Dr. Ali,
Yes.
I got 0.4.
0.4. 0.4.
Yes, sir.
So you have used the first equation, right?
Yes, sir.
And what was the VG value?
I got 2000.
2000.
Yes, that's right. Yeah.
And that R braking resistance value is 0.4.
So it looks like 0.1273.
We got 0.4 when substituting VGS 2000. And
Okay.
firing angle alpha is 0.
Alpha is 0, so there is pi. So and then you say
The pi and pi get cancelled, then 10 megawatts divided 2000 whole square divided by 10 megawatts, we got 0.4.
yes, that's right.
Yeah, they're the same.
Yeah. So therefore Amani also you got 0.4, right?
Yes, sir.
Yeah.
Yeah, Dr. Ali. It should be 0.4.
That's right.
Yeah.
Yeah. So
Yeah, it's 0.4.
yeah, same value. Yes. Okay. Yes. Kamana, did you get same value?
Yes, sir. 0.40.
Yes. Okay. Very good. Yeah. That is. Yeah. Okay. So now, Sindhuja, did you get the same number?
Yes, Dr. Ali.
0.4. Okay. Very good. Yeah. Now everybody read number 2, and then in this case, again the same question. What would be the value of the braking resistor? Again the same question. But then which equation to pick up for question 2? Read question 2 and then pick up the appropriate equation and then solve the problem.
Dr. Ali, is it 0.364?
0.364.
Yeah, I got 0.364.
Looks like a little bit deviated. What was your VDC value?
1909.
1909.
Yeah, 0.85.
So I think BDC would be 8485.28.
84. Okay, let me check one.
Oh, it looks like wrong. So, no, so
No, did I forget to? I forgot to divide by pi. I'm sorry. Yeah.
so do and divide by pi.
So is it 2702.31?
The VDC value?
Yes, because we have to use 3 bm by pi, right?
Yeah.
Cos of phi equals to 1.
Yeah, that is fine. But what is your VM value?
It should be 2000 by into root 2, right? 2000 into.
No. So everybody, that is the mistake. See, this is the three-phase synchronous generator.
Oh, I see.
You see, everybody see that. That's why your mass divide. Like number one is single phase, but number two is three phase.
I got it.
Yeah, Lakshmi.
Yes, Dr. Ali, I went there wrong.
Yeah. I'm guessing so.
Yeah.
Yeah. That's why, like your VDC, I got completely different than both of you. So you told again different number. Yeah. So let's check. This is the three phase. So probably you have the wrong VM value.
Then is it 0.12, Dr. Ali?
The final resistance value?
Yeah.
No, it should be 0.243.
Okay.
Yeah, so the once again loop the calculation. Again, maybe there is another mistake. Yeah. First, tell me what is the voltage value that you got at the beginning?
Is it 2000 divided by root 3?
No. Can you not relate to that? Or what is the 10 MVA in the problem? What is the 10 MVA? That is the apparent power, right?
Yeah,
so it should be.
It is apparent power, and then 5000 ampere is the rated current, rated line current.
Yeah.
So
Is the VM value equal to 1154?
Yeah. 1154.70. That will be.
Yeah.
So therefore, everybody see that is the three-phase apparent power, 10 MVA. And then 5000 ampere is the line current, RMS value, of course. So the apparent power is root 3 VLIL, apparent power value. Right? S equal to root 3 VLIL. So did you write S root 3 VLIL? And then, so BL value should be 1 on 54.70. Manoj, did you get it?
Yes, Dr. Ali.
Okay.
I'm on it.
Okay. Sindhuja?
I'm working on it, Dr. Ali.
So I'm talking about the voltage that you have to calculate at the very beginning. Yeah.
Oh,
I am not talking about the VDC still. Now, before the VDC, you need on voltage, line voltage.
I got that 1102.
Oh, so I'm sorry, that is the wrong. So you see, oh, look that once again at the very beginning problem too. 10 MVA is the three-phase apparent power, and then 5000 is the rated line current. So equation will be AC equal to root 3 VLIL. Apparent power equal to root 3. Line voltage multiplied by line current. So therefore, apparent power is 10 MVA and line current is that 5000 ampere. So by using that equation, AC equal to root 3 VLIL, you have to get the VL value, line voltage first.
Okay.
Yeah. So write the first equation, AC equal to root 3 VL IL. That is the equation for three-phase apparent power.
Dr.
Yeah.
Ali,
Yes.
VDC is equal to 1102. Am I right?
The VDC.
Yeah, equal to 1102.65.
No, it looks like I got on 559.39. Manoj, what was your VDC now?
So for the second one, I got 1154.7. That is the BL.
Right, that is right. And then Lakshmi was talking about the VDC. I mean,
So it's gonna be 3 VM by pi.
yeah. So what should be that number?
Just give me a moment.
Lakshmi, you told that is like low number. Then I got 1559.39.
Yeah, I got 1102. Like when I substitute 3 into 1154, that is VL by divided by pi.
Okay.
And
So no. In the VDC equation, look, oh, that is another wrong thing then, yeah. Sorry. So you see in the VDC equation, 3 Vm by pi cosine of alpha, right? So in that equation, Vm is that Vm is not the RMS value. That Vm is the peak value.
oh, okay.
That is the peak. But the VL that you are getting, that is the RMS value.
Okay.
So therefore, this means you have to multiply by root 2.
Oh, okay, Dr. Ali. Yeah.
So I got 1159.39. I mean 1559.39.
The VDC. Manoj, you are talking VDC.
Yes. How much you got?
1559, 1559.39.
Okay, let me check again.
Yeah. Let me, yes. So please check again.
Yeah, Dr. Ali, I got 1559.39.
Very good. Yeah.
I got the same one. I told you that one.
1559.
Yeah, 1559.39.
Oh, okay. But it looks like 1159. Yeah, okay.
Is it 1559 or 1159?
1559.
Yeah, that's what I got. 1559.39.
Okay, exactly right.
Okay.
Yeah. So then up to that, that's right. Yeah. So Lakshmi.
Yes, Dr. Ali, I got the same value 1559 and I'm working on RPL.
So everybody understand, like you made two mistakes at the very beginning. Probably you just divide the 10 MVA by 5,000. And then the second mistake was that in the equation, keep in mind 3 Vm by pi, that Vm is the peak voltage, not the RMS voltage. So keep in mind, otherwise again in the exam or homework, you will be making mistake. Oh, so I did not explain those equations. I thought that you all know those things. That's why I did not specifically mention when I was showing the equation. So everybody note down that the 3 Vm by pi, Vm is the peak value of input line voltage. So this means once you are calculating line voltage, which is 1154, you have to multiply by √2. That will be the Vm. Okay, so then what is the final value of the R, the braking resistor?
What do you have?
It's 0.24.
0.24, right? 0.243.
2431.
Yes, exactly. Yes. Now everybody in the same page. Amani, are you getting?
No, Dr. Ali, I got 0.1214.
The braking resistance value?
This is my R value.
Oh, okay. Again, you need another calculator. You have to buy another calculator.
Maybe that's why, I don't know.
So
So
what,
my V
what was
value,
what
L
was your
value,
VL value? What was your VL value?
my V value for the line to line, it's 2000, and VM is
No. So that is wrong. You see, that was the 2000. That was for the first problem. You look the very first line of the second problem. It is three-phase system. First problem was for the
yes,
single phase system. So
yeah.
therefore, for the problem two, for the three-phase system, we have to use equation S equal to √3 VL IL. So you will be getting VL value 1154.7.
I did that and I got something different.
Ah,
So yeah, I did that. I got
What are you doing?
3,564.
so
So can you please, Dr. Ali, do it on the while using the whiteboard? Can you use the whiteboard to show me? Thank
yes,
you.
sure. Let me see. Hold on. Clean up this thing. So at first you see, everybody, at first, this is the equation for problem number 2, the first equation. √3 VLIL. Look this one. So this IL which is given, which is 5,000. This is 5,000. The S value is, that is the 10 MVA. So this means 10 multiplied by 10 to the power 6 volt ampere. So therefore, you will be getting this VL value, which is 1154 point approximately 7. This is in volt. And then you write that equation. VDC 3 Vm over pi, and then cosine of alpha, the basic equation. But because it says full conduction, so your alpha is 0 degree. But then this Vm, you see, Vm is this number multiplied by √2, because this is the RMS. This VL is in RMS. But this Vm here, that is the peak. So this means to apply in this equation 3 Vm, this means 3, this number multiplied by root 2, and then pi cosine alpha alpha. So then you should be getting VDC on 559.39 volt. And then use that last equation, that PBR, that VDC over R, sorry, VDC square R. That is the RBR. So therefore, this value will go for the VDC. If you do that, and then the PBR value, it was the 10 megawatt. This was given. This was 10 multiplied by 10 to the power 6 in watt. So therefore, finally, your RBR value, this value, it should be 0.243. Sorry, 0.243 approximately. .243. Amani, did you get it?
Yes, Dr. Ali, I saw my mistake right now. I used, instead of 3, I used the square root of 3.
Oh, in the equation, VDC equation?
Yes, it's
Oh.
math mistake. Yes, mathematical mistake. Here, mine. Yeah.
Okay.
I used square root of 3.
Okay. So,
Thank you, Dr. Ali.
Sindhuja, can you follow me?
Yes, doctor, I got it.
And now, did you get this result, 0.243?
Yes, I got it.
Okay. Venkat?
Dr. Ali,
Yes?
Venkat just texted me that he's having some internet issues, so he's trying to reconnect back.
Oh, okay.
Yeah.
So he consumed so much power so that he caused the instability of the system, and then I'm just kidding. Okay. So then I'm going back to the problem. Okay. I think we are, sorry. Okay. Now everybody read number 3. Read number 3. And then solve it. Can you see
So
number?
I got 0.1556 ohm.
Just a moment, let me see. I have. Oh yes, on 0.1556 ohm, right? That is correct answer.
Yeah.
Okay. So everybody please try number 3, and then you should get the answer 0.1556. And then can you see the tradition, the first one has 0.4, the second one problem 0.24. In the third problem, again, it is like 0.1556. So is everybody doing number 3?
Yes, Dr. Ali.
Yeah, please, yes.
Dr. I got it was 0.1556.
Okay, yes, that's right.
Mhm.
So therefore you see the difference among three problems. Just it depends on, so I mean by reading the problem you can understand which equation to pick up. I mean the same problem, same thing, braking register and even the ratings, everything is the same. Just it depends on the what is the braking register control technology. That will govern which equation to pick up. That's the thing. Kamana, have you got the same result?
Yes, Dr. Ali.
Okay, okay, good. Amani,
Yes, Dr. Ali.
you got the same 0.1556.
Yes, sir.
Okay, and Sindhuja,
Yes, Dr. Ali.
you got the same result?
Yes.
Okay. And Lakshmi, has Venkat come back or still is trying to connect?
Dr. Ali, I think he's still trying to connect.
Oh,
He
okay.
just texted me and that's
Oh, okay. Fine. Um, so I think already 6:50. Now I had a couple of questions. Maybe we can talk one or two and then we can close for today. Everybody see, there are some questions. Following a fault, a thyristor-based braking register can maintain the transient stability of a multi-machine power system consisting of synchronous generators supplying power to a grid. That we learned and we solve problem. However, a braking resistor just dissipates power and produces heat, right? Yeah. Then how does it ensure stability? So everybody read the question, understand the context. So we learned that the thyristor based braking resistor can maintain stability. But what I am saying that however braking resistor just dissipates power, right? It just consumes power and then that consumption goes in terms of the heat. That is not only this braking resistor, that is the function of any resistor. Resistor is only happy, satisfied with the consumption and producing heat. And then the component is happy. It cannot do anything. So while a component is getting heated up, and then how does it maintaining the stability? What it is doing then actually? So then explain your answer. So how would you answer this question?
I think if we go to the string equation, then it is maintaining the constant electrical power, PE,
Right. Therefore,
by dissipating the.
right. The answer is that even though it is like producing heat with the power consumption, but it is actually providing power. It is boosting up the P. That's why it is maintaining the stability. And then the other thing is that in real practice, if you read those BPA and then Peace River transmission system, as I told you, or if you Google braking register, in fact, even though it is get overheated, but immediately those dissipates in air because this is exposed in air. So therefore, in one, and then the operation is not too long. It is only for the transient moment, maybe only 1 second or 2 seconds, or hardly 5 seconds. So therefore, it is getting heated up. That is true, but then immediately it will start releasing heat, and then ultimately it will be cold at some point. So that's why heating is not the problem. The main benefit is that it is providing the P. So that's the right answer. So everybody? So do you understand the question and answer, everybody?
Yes, Dr.
Yes, yes. So therefore, like I'm confusing him. I'm creating confusion that okay, braking resistor is produced, then how it is helping? Because it is providing the power. So heat consumption, heat production is not a problem. That's the meaning. So question number 2, everybody read. If suddenly a large load is connected to a power network, how will the system be affected? So will there be any stability issue, you think, if suddenly a large load is connected to a power network? So how will the system be affected means what will be the stability status? That is the question. And in such a case, can a thyristor switch braking resistor or a capacitor help maintain the stability of the system? Explain your answer. The first one is, if a large load is connected, then will there be any issue?
Yes, there would be stability issue.
So what type of issue will it create?
So it will create the frequency stability issue.
So what will happen to the frequency? Will it increase or decrease, or it will remain the same?
I think if we connect the load, then I mean the speed will be reduced, right?
Yes, yes, yes. For everybody see the once again the swing equation. So you are increasing the load than what was available. For example, it was 100 megawatt that was available, and then PM was your 100, but then you are increasing some load suddenly 10 megawatt, 20 megawatt. So therefore your result is getting negative. So what is the meaning of negative? Instead of acceleration, system will be decelerated. And deceleration means your speed will go down. And then ultimately frequency will go down. So therefore definitely that is the, definitely yes, there will be stability issue. And then I said that under such condition, in this case, can a thyristor switch braking resistor can help or a capacitor can help? So explain your answer. So then what will be the solution?
Of course, that first thyristor switch braking would help because capacitor will only provide the reactive support, but we need the active control. I mean power control. So I think we should use thyristor switch braking resistor.
So if everybody, do you agree with Manoj? Is his explanation right? Everybody, do you think? Kamana, do you agree with Manoj?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay, so therefore, so see that you are putting, therefore then go back to the equation again. So what Manoj initially you replied that if we inject power, right, then the system will be decelerated, right? Yes, then the speed will go down. So therefore already you inserted load, then again you will be connecting the braking resistor. You see that you already increased the load, you injected the load, and that caused frequency and then speed stability issue. So then still you will be using the braking resistor because braking resistor will increase your this power more and more. So the result will be negative and negative. So
I see now. Okay.
therefore, I know Kamana will support you. Then why everyone? Kamana, do you understand?
Yes, Dr. I
That's
get
the
it.
first I asked you that do you support, but immediately you supported without looking at.
I mean, I completely forgot the swing equation. I just, went up towards the, control view point. So I just lost the sequence here.
Everybody, can you understand what I'm saying? Therefore, see what we learned today. Your goal of your function of the braking resistor. When P is low, then you use the P braking resistor to be stopped. But the question was that everybody, question was that suddenly large load connected. This means system was providing the required power. It was meeting the demand. So there is already P, and then you are injecting. Then if you add the braking resistor, system will be decelerated and decelerated. So in that case, the Manoj, therefore you answered other thing that what you said, what capacitor can do, you said?
So it will give the reactive power support as well as what else?
What is the meaning of that injecting reactive power and what it does, what capacitor does?
So you just do the voltage stability thing, or
Exactly. I mean, capacitor injecting means like you are improving the power factor, right?
yeah.
And improving the power factor means you are bringing back the voltage. So actually, you see that what will happen when you are connecting the large load in the system, this means your system is overloaded. So therefore, not only the system will be decelerated, I mean, speed will go down, frequency will go down, your voltage will also go down. You understand? You are
Yes.
overloading, you are overloading the system. So your voltage will also go down. Yeah. Therefore,
Voltage collapse.
voltage collapse. Therefore, if you connect the capacitor, it will provide the capacitive reactive power. This means it will improve the power factor. Voltage will come back. And if voltage come back, gradually then your on the speed, frequency, other parameter, indirectly they will also come back. Yeah. So that's why you see it's I have made you confused in that in such a case, can you choose the braking resistor or capacitor? You see, it depends on what is the issue. The issue is that you suddenly connected the load. But if the problem was you suddenly disconnected the load, remove the load, then you could use that braking resistor to compensate that reduced amount. But you are like increasing, and then thyristor means again you are increasing, meaning that you are decelerating the system. System will be stopped at some point. It cannot produce voltage, and then generator might be stopped if you continue putting the power and power. Okay, so I like to stop here today. I think the Venkat is also got disconnected. I'll be discussing the other question next class. Okay, so is everybody fine? Does anybody have any question, comment?
I think you're good, Dr. Ali.
Okay, okay. So therefore keep in mind, we will start from number 3 in next class. Okay, so at this point,